Why?
Well, the story begins in 1973 with a report out of Warsaw that palladium and deuterium had a higher transition temperature than palladium with hydrogen. That was considered a mistake, and my master's thesis in physics was to repeat the work and see if indeed there was a mistake. But by 1975, I had completed my thesis, and I found that indeed deuterium in palladium has a higher transition temperature than hydrogen in palladium. I got my degree, I moved on. Later years I went to MIT for a PhD. I worked at a government laboratory just outside of Boston. In 1987, there was a great hue and cry when high temperature superconductors were discovered. And my laboratory broke into 3 groups. We each took about 10 days to make the new materials. And after we had made them and showed that they worked, I said, well, that's enough for me. But my lab director said, Brian, we're putting you in charge of just trying to find out, determine where these new materials were going. And I said, why me? You know, I'm just a schmo. I don't know anything about superconductivity. They say, well, you're elected because I did my master's thesis in '75 at low temperature superconductivity. Well, you know, that's what happened. But I became the lead scientist for the entire Department of Defense because they were just allowing the Air Force to run with it. So it became my job not to figure out the superconductors, but to figure out somebody who did figure it out. And I had a seminar series where I paid people a ferocious amount of money to come in and lecture in my laboratory. I would pay the equivalent this today of $5,000 for 1 hour. It was ridiculous. But I had the budget, the education budget, and it was still a Cold War. And it didn't work. After about 8 or 10 of these discussions from people from around the world, I didn't understand what they were saying. It sounded good, but didn't make any sense to me. And I was about to give up when I went to Harvard Square, where there's a bookstore with a new book on superconductivity, and I went to buy it. And I said, if I can't understand this after reading the book, doing every problem, and then hiring the author to come to my laboratory and teach me for a week, if I can't understand it after that, then I quit. And I'm not going to be a scientist anymore. But with the book under my shoulder, I walked across the street, and there at Old Bond Pan was my old professor from MIT named Keith Johnson, the only theoretician in the material science department. And I asked him, Keith, did you know anything about superconductivity? And like all theoreticians, he said, I solved that problem back in '83. So I got his paper, which was impossible to understand a word. And I wasn't in any better shape. But I had a construction company I was a partner in one, and his wife was an architect, and we had reason to get together because she had a whole cadre of people who wanted to have houses built. So I showed them places to do that for about 6 months, and Keith would come with them, and I would ask him question after question about his thesis on superconductivity. And indeed, he had solved the problem, and he used 6 different materials as examples, and one of them was palladium, hydrogen, palladium, deuterium, topic of my master's thesis and for Pons and Fleischmann. So I finally understood what he was saying in '88, and we told my lab director that we should not fund these new materials. They should ignore them because that which makes them high temperature also makes them too fragile for operation. They're inherently unstable. So they made that recommendation to the Department of Defense, and all funding was dropped. And to this day, 20 some odd years later, there's never been a single device that used one of those high temperature superconductors because they're just too fragile. But the knowledge gained from understanding why a superconductor does what it does allowed me to take this new way of looking at materials into the world of nanotechnology, where that was my absolute passion starting in the '80s. So it allowed me to understand nanomaterials in their vibrational modes in a very different way that other people just don't have any idea about. And that led to a discovery saying that this magic in nanomaterials, when they're partitioned or processed between about 3 and 12 nanometers, or you can say 5 to 15 nanometers, but everything at that size regime has magical properties, and everything does. There's no exceptions to it. So I knew that, and I was taking that knowledge into a lot of different fields, including light emission. And we were making light-emitting polymers with those kinds of materials. And at the time, we were leading the world in efficiency. But in 2009, right at the beginning of 2009, I had heard about Arata had made a presentation in Washington on August 2008. And he got up and said he was getting not useful, but repeatable thermal energy out of nanopowders in the 5 to 15 nanometer size regime. And right after him, another fellow got up from the same university named Akito Takahashi. And he said, we didn't see any thermal effects. Who are you going to believe? The strong young man or the 85-year-old who's in a wheelchair and you can't understand a word he's saying?
Me, I believe the 85-year-old.
Well, I had never heard of him, so I had no reason to believe it. But I said to Takahashi, well, you failed because you said your particles were in the 20 to 100 nanometer size regime, and you're out of the magic zone. So as soon as you get to 5 to 15, you will see the effect. It took me the whole month of January to convince him, but I did. And before the 20th anniversary, on March 23rd, he was presenting it in Salt Lake City that yes, indeed, he was getting repeatable excess energy out of the nanopowders because he went to that magic size regime. So I got money from the Electric Power Research Institute to really study these things. And I said, I don't need a salary, just give me money for the materials. Materials were very expensive, so that's why I was the only one who had this opportunity. And I went for several years, and we found different alloys worked better than others. And nickel and hydrogen work just as well as palladium and deuterium if you process in the size regime. But there's very few places in the world where you can do it. There's only one in the United States, 2 in Japan, and 1 in Russia. You cannot get these materials processed anywhere because nickel and zirconium don't like each other. And if you try to melt them together, as they cool down, they'll segregate away from each other. But if you take them from the liquid phase and you instantly cool them, you splat cool them at like 1,000 degrees C per second, you freeze in the liquid microstructure such that when you then bake it in air, the zirconium, wherever it is, turns into zirconium oxide, and the nickel agglomerates with other nickels, isolating nickel islands in the middle of a ceramic zirconium oxide. And that process was invented in Japan in '92, and Arata used it, and I used it, and in the United States you can get it done at the Ames National Laboratory, where they can take any alloy you want, they arc melt them together, then they splat cool them, and it comes out a ribbon like tinsel. It looks just like off a Christmas tree. And you get about 200 yards of it. And then you bake that, grind it into powder, and then you perform the Arata experiments. And it works quite well.
And the baking I saw in your report was to oxidize the metals, right?
It oxidized the zirconium. Zirconium loves to be zirconium oxide. Nickel doesn't like to form an oxide. So that's the beauty of it. And so that's, I don't know if you saw my EPRI report. It's free if you can pick it up by just Google.
No, I read it all and refreshed myself before the call. But for those people that haven't read it yet or might not understand it, it's just as well to go over things.
Now, I was all set to do high voltage pulses through the powder. That was my goal for a couple of years, and I finally got a power supply that could do it. It could go up to 2,000 volts and it could give you anywhere from 1 to 10,000 pulses per second. I found out that the breakdown between the powder and the electrodes was about 600 or 700 volts. So I set the power supply to 1200 volts so that every time I went to 1200 it would break down. And I turned on the power supply, and after 60 seconds it fried because there was so much current coming when it would break down that it overheated the power transistors, and it burnt out. And I wept and said, what am I going to do? You know, this was a gift. It was a black box to me. And it was a one-of-a-kind power supply. To replace it would have cost $50,000. So they sent a man from not too far from me, about a half hour, Pelham, New Hampshire. It's just the first town across the Massachusetts border. The fellow named Arthur Manillas came to help me fix the power supply. He brought it back to his home and brought it back the next day, and we ran it, and it ran for a good 90 seconds before it burnt out. So he said, let me take all the equipment. He took the power supply, he took my dewars, he took my powder, my vacuum pump, he took everything back to his house. And after a week, he said, come on up and look at it. And that's when I found, he introduced me to his electric car. Now, are you familiar with this part of the story?
I saw your, you did a presentation, I think, in 2011 where you talked about it. And as I understand it, it was an electric car, and he had a circuit in there that was able to recharge it passively, or you know, recycle charge to generate more charge. I think that's what I understood from what you presented.
Yeah, for a physicist like myself, that's an absolutely bombastic claim. You know, how can that's a perpetual motion device? And I was not prepared to accept anything. But it was sitting in a car, and there was a 160-volt battery that weighed about 300 pounds of lithium ions. But electric cars, they have to run a lighter, a clock, a radio, and they all run off 12 volts. So there was a circuit in there that went from 160 down to 12 volts. And that 12 volts was powering this device the size of a briefcase. It was then sending high voltage pulses above 160 volts back into his power supply. And it was charging at a small rate. That is, it was enough to give him, the car would go about 75 miles on a full charge, and this would give him about another 6 miles. So it wasn't running his car by any means. So I said, well, he won't part with his car and let me drive away with the thing, but we decided to measure the recharging rate by basically sequestering the car. We covered it with a tarpaulin, built a fence around it, put cameras staring at it so no one could go near it, and we let it go for a week. And indeed, the voltage crept up on a steady rate, and it went from 69% charge up to 89% after a week. And I was amazed by it, and I wanted to do more testing, and he allowed me to do more testing. And the key, not the key, but one of the aspects of the device is a big slab of ferrite, a brick-sized piece that's wound with copper wire around all 3 axes. And he was sending signals into that, and somehow there was some magic happening. And I don't know what. I was trying not to pry. I was trying not to, learn his secrets, just to find out if indeed he had any. So I ran a 60-watt bulb for 4 days while we're running data logging voltmeters, and sure enough, 60-watt bulb for 4 days would deplete most batteries, and this one, the voltage continued to rise. So it was still making power in light of a 60-watt drain. And if you leave the light in your car on overnight, you know you're not going to drive the next day.
I've done it.
And that's a 15-watt bulb. So I had 60, 4 times as much, and it went for 4 days, and it was at a higher level of charge than when I started the whole device. So I got very excited, and I brought a money man in to meet him and to say, he's willing to put up $5 million. We just have to go through the same test I just did. And that's just getting started. Well, he met with his family, and they were quiet over Christmas, and he said no, he wasn't going to take money from anybody. He was going to continue to work on it by himself. And we thought that was odd, but he let me continue testing, and all the testing was looking good. Until one day in April, a Sunday morning, he called me and said, "Gee, something happened. The battery spontaneously overcharged and burnt out some of the batteries. That his energy has somehow gone into his battery from an unknown source." And I didn't know what to make of that. So then we did more testing through up till about July, when he said he didn't want to do any more testing. He was going on vacation. He'll restart them again in September. And then September 23rd, he called me saying, "Yeah, okay, it's time. I'm not going to take the full year. You and your team can take over and take the technology forward." And 2 days later, he had a massive aneurysm. And he was near death, but he's alive, but he's vegetative. And he didn't write any of it down. He's told us he wrote it down, but he never did.
Has he left the circuit intact?
No, the circuit was not intact. He was redoing it, so it was, in partial assembly. And furthermore, the company, the family called me to make sure it was turned off because they didn't understand it. And I turned it off on September 26th. And the rule was, if you let these things sit idle, the magnetic circuits degrade. And sure enough, when we turned it back on in January, it wasn't working. So I got the equipment from the family in August, and we tried to run it, to reassemble the few things we were missing. It was just running on 10 watts, and the battery was slowly decaying because they're a very big battery, and there wasn't much of a load. But after 2 days, now the first day the battery voltage, the battery voltage was at 63.1 volt. It went down to 63.02. The next day it went down to 62.94. So it was going down at 0.08 volts per day. And on the third day I went out at 7 a.m. and I came back at 10, and the battery voltage had spontaneously hopped up by over a volt. And it took 2 weeks of running that to get back to that same level. We don't know what happened. I wasn't recording at the time, and I was just data logging manually. So that was an event similar to what happened to him on a Sunday in April. The energy had somehow gotten into the battery by means that we don't understand, and I have no idea.
So by this time you changed the location of the device, and it was now running without any knowledge of him, that it was running at that time.
Now it's not running, showing any over unity at all.
Right.
But we took the device, which has 5 solenoids that can be tuned individually, and we didn't do that. I didn't tune them individually. I just found 5 settings, and we didn't go back iteratively to find out how one affects the other. If you tune one, what does it do to the others? We didn't do that, so that's what's next in line. And at the conference at MIT, which was held, 11 days ago, when I was making my presentation, a fellow at the back of the room said he knows what's going on. He has been seeing this kind of behavior in iron materials for 20 years. So I'm very excited about that he thinks he understands the process. And he thinks it's just acting as a big antenna, to extract energy from the environment. And I live 125 miles southwest of the biggest radio station in the world, in Port, Maine, or Cutler, Maine. There's a 2 million watt transmitter that transmits signals so submarines can hear them around the world.
Yeah.
And so that's the biggest one in the world by a significant margin. And he thinks we're just extracting energy with this circuit from that source.
Well, I mean, there may be an argument for that. There's that whole group of people, I think, Konstantin Mail, who's recently written a book in German on his theory for DD fusion. I remember seeing him saying that his whole community were harvesting electricity from transmissions to light their gardens and stuff, with big, fairly hefty bulbs, until the electricity board came round and told them to take them all away.
Yeah, I think that's a wives' tale.
Well, he seems to be fairly sure about these things, but I don't know. My brother is pretty good at wireless power transmission, and he uses it. He's designed some for his nano aviation vehicles. So I don't know, but I think the guy at the back of the room might be closer to the truth. And if it's a case of tuning very carefully resonant circuits, you might just be trying to tune into a specific power source that maybe wasn't as strong at your location as it was at his. I don't know, but it's all speculation without the man's particular opinion, and sometimes these people don't quite know why they get things to work, just that they do.
Well, Arthur Manellis didn't know why for sure. He came to my house not to help me fix my power supply because he had heard that I was intent on doing high voltage pulses through nanomagnetic materials. Now, when I told you that there was magic between 3, 5, and 15 nanometers, the magnetism is very different there too. In 2006, at the Max Planck Institute, a thing called magnetic vortices were discovered. Little magnetic storms.
Yeah.
And I think that's what we're creating in the errata material. They're little magnetic storms. And, well, how do you get more energy out of them? Well, I had one runaway reaction. And everybody who's been in the business seems to have had one runaway. And my runaway happened with the only material, and I didn't know it at the time, but it was, I had allowed the powders to grind and grind and grind and grind, normally for 3 days, but I let them go for 2 weeks. So the particle size was smaller, and I didn't think that was important, but now people are coming out saying, oh no, the macroscopic particles, the size is really important. And so I think that's something to take into consideration. And the magnetic interactions between materials could just lead to somewhat we call cooperative behavior. But I don't know. I just know I got 14 experiments in a row to show excess energy. But then I got 4 in a row at the end. My last 4 measurements did not show excess heat. They showed excess cooling.
Is that the ones where you use titanium?
Yes. Now titanium wants to be an oxide as well, make titanium oxide. So I just substituted a certain amount of the zirconium for titanium and led to cooling. Now when I did the Manellis device, I put a thermistor, 3 thermistors in the trunk of the car, and one right on that ferrite billet, which acts like the core of a transformer. And it ran 3 to 5 degrees C colder than the ambient the whole week. I didn't expect it, anticipate it, but that's what we measured, with a high degree of precision. So there was no mistake.
So maybe are you suggesting that it might be some sort of thermoelectric generator, but using low environmental heat?
I don't think that's primary. I think it's just one of a corollary or just part of the behavior.
Mm-hmm.
Now Manellis did all this work because he heard of a fellow named Floyd Sweet who had done it back in the 80s, and the people who watched him do it claimed that his billets would get down to would cool by 20 degrees C. He was making more power. So there was a lore about that that I hadn't heard about. I never heard of Floyd Sweet until after I started the Manellis testing, and he told me that's why he did it. And so he took it to the grave, and Manellis has not done much better. And so we're still hoping to just show by various kinds of tuning that we can get back to the over unity and then try and learn something from it.
Well, it's a great shame to hear of another potential loss, particularly when there's so much conflict in recent years and power manipulation going on because of energy issues.
Did you see in the news today that Mats Lewin from Scandinavia wrote they published a book about how he feels about Rossi?
I did. I haven't read it yet because I wanted to focus on our conversation. I know Matt quite well, and I was in direct Skype link with him when he was with Defcalion last year during ICCF. So I was and I have had a conversation also with him. I think that he's been in contact with Rossi since pretty much day one, and obviously he's Swedish, and Elforsk is Swedish, Vattenfall. So there's a good chance that he has or facilitated some of those connections. And I think he if there's going to be an authority, he's going to be one of them on the situation. So I think it's worth a read. I'm not sure that there'll be masses to learn from it for those people that followed the story closely, but for those that have been there for quite some time, those that are newer, I think there'll be a lot to learn from his writing.
If you had to put a place a bet, what odds would you give people betting that Rossi has something?
I think he's done remarkably well if he's defrauding people to get as far as he has. I believe that there are people that paid for licenses that would have rather have seen any version of the technology that they could easily sell, or even a version of the technology that could be publicly visited so that they could sell on the strength of the licenses they purchased. I think with the size of the industry, it distorts everyone's mind. The pretty much is few industries larger than energy. And it's difficult because I know someone personally who is almost identical character and behaves in exactly the same kind of way as Rossi, but this individual absolutely 100% does what he says he does. So any reference to his character being or the way he acts, for me, is not a red flag, because he's just a classic inventor, but I suppose a more seasoned scientist might call him an Edisonian approach inventor. But I think he made a wise decision, if that's what he has done, by bringing in more structured research and resources outside of his control. And I think that's a huge learning that someone with his abilities and approach to science can do to learn to step back, give over what you know, and let others take it forward. And I think with Morellus' device, I think did I say that right, Morellus? Manellus.
N-E-L-A-S.
I think Rossi has to be given credit for what would seem the process of passing the technology on to a larger organisation, and I think that shows a level of confidence. So when I was fortunate enough to take myself to ICCF 17, by day 2, for me the biggest problem in the industry was that people weren't cooperating and they weren't sharing enough, and I was very worried that I wanted to make life decisions on whether the technology was real or not, and make my decisions based on either outcome. But the ambiguity was killing me, and and so I saw that I understood pretty much everything that was said. I'd been following it from a long time, and science in general, and it became clear to me that someone had to start sharing their technology to a point where it could be challenged and replicated and tested and even improved. And for us, it was very good that Francesco was willing to have his technology challenged, and we're still in that process of challenging that technology. It was never meant to be superpower, but anything over unity that's repeatable is a very interesting demonstration, and it's something to work off. And I guess that brings me back to where we are now. We're in the process of starting a new thrust, some of which Celani's technology will segue through, because as far as we know, it's never been tried in certain kind of regimes like triggering with discharges. So we can test it in those kind of environments moving forward. But we would like to test some sort of powders that have shown any level of repeatability. Like I say, it's for us. It's not so important that it's huge kilowatts right now. It's just that we can demonstrate repeatedly that an outcome can be achieved. So as of today, the high voltage triggering circuit, as conceived by Stoyan Sarkachev, it's on its way to Minnesota, and it has a specification of DC 20,000 volts capability, up to 20,000 volts capability, with a up to, I think, 15 pulses per second, and I think an AC it's up to 40,000 volts and 30 cycles a second. Now, when I was looking at your patent application, which I'm quite interested about talking about, you're looking at much higher frequencies and changing the duty cycle on those pulses. Is that right?
I had none. I wanted the capability. I didn't know what I was going to do. I just wanted a power supply with maximum variability.
Okay. So have you built this device, or you built a device that's capable of producing?
No. A fellow from Boulder, Colorado, who I had met only once. He came to my lab and was impressed. So he had a power supply company, and he built it and shipped it. The thing weighed about 80 pounds, and he shipped it to me just because he wanted to see if he could help.
Oh, sorry. Is this the power supply that then promptly failed?
Yeah.
And
it wouldn't have failed if we had recognized we just had to put an inline resistor to limit the current. I didn't know that, and I was, that made sense in hindsight.
Yeah, I think something with plasmas, it becomes a superconducting channel or something, doesn't it? So you have to, it's an initial high current, and then you dial the current right back, and something like that. I'm not a power supply expert either. I'm largely a facilitator. Okay, so I'll just try and see if I can capture some of the questions we had. The powders that you were using, I guess we're probably more interested on picking up the story where you left off, and I think you said you were using some nanometric powders provided by Quantum
Sphere. Quantum Sphere.
Quantum Sphere. Very good. And that you were seeing sort of Rossi-Defkalian ballpark figures in the excess heat in the one test that you did?
Well, I saw 20 watts. Okay, that's a long way from Defcalion and Rossi. And I don't know if it's repeatable. That was the end of my budget. That was the end of the contract. So I didn't do any more. And I gave the powders away to Mitchell Schwartz. Does you know that name?
I very much do know that name, yes, and I'm in semi-regular contact with him saying that he's quite happy to send us a device. Still waiting for it.
Yeah, I wouldn't hold your breath, but recently he's been doing experiments where he does a capacitive discharge through a coil of wire adjacent to the material.
Yeah.
That leads to a very large B field, 1.5 Tesla. So it rises and falls in the scale of 100 microseconds. But just one pulse is enough to improve the performance of his excess heat by a factor of 10, and it goes for hours. One pulse.
So do you think that's essentially what Yonghi Kim was saying or speculating, that the charge generated through the conduction channel, which is the plasma in the center of the Defcalion reactor, creates a very large magnetic field, so effectively that discharge becomes its own conductor, and then that is doing something to create what he calls magnetic traps for the incident Rydberg matter that forms Bose-Einstein condensate, and then there is events occurring in those what he calls magnetic traps.
I do believe that magnetism is at the core of all this. I can't say any more than that, other than Mitchell's result. Then Larry Forsley and Pam and Boss, they find that they get particle tracks only when they have a magnetic field on, not when they have it off. I'm just trying to think. There's a few others like that are seeing these fantastic effects.
Yeah, Dennis Cravens, I think, believes that.
Cravens, yeah.
Yeah. So.
Let's as well.
Yes. Well, they kind of work together. They're not the same person, though, as I was told. Yeah, I mean, we started down a route before the kind of like winter hit Minnesota, of having some three coils around one of our Chelani reactors. We haven't really explored that, but we've got a new guy starting there, and so maybe he can explore that setup. I guess from our point of view, then, so you haven't got any of this powder. So what do you have?
I have, powders that have got, palladium,
mm-hmm.
that I may have used with deuterium or hydrogen. I just don't remember how I have them marked, but I've just got vials of this stuff.
Right.
I think some of it would be worth regrinding. I wouldn't say do anything with them because nothing was spectacular. But if you ground it from its 75 microns down to 15 microns, you may have a runaway or see a great deal more heating than I did.
Okay. My personal expertise is 3D modeling. I've been a 3D modeler for maybe 24 years now. I am working with one of the leading manufacturers of direct laser metal sintering, a German manufacturer called Concept Laser, and I'm looking to make a fairly flexible reactor design. One of the aspects that I would like to put in there, and it was suggested by one of our followers, that we put it onto the Chelani cells, which was to literally strap some piezo transducers and have some nanopowder inside our Chelani cells and try and fluidize it type thing. Well, I'm looking to create a fluidized window, and I noticed you said something in your patent with respect to that as well, using ultrasonics. Was it just to fluidize, or was it to create shock waves through, or?
It was just a fluidize.
Okay, and is that something that you've tested, or is it speculation?
I had been preparing to do it for over 20 years. I had followed the workings of a fellow named Peter and Neil Grinnell, where they were doing capacitive discharges through metals underwater and getting over unity. And he was, lived in the neighboring town, so he became a mentor to me since the early 90s. And it was repeatable, it was over unity, and it was not worth anything. We couldn't figure out how to manipulate it and do anything good with it. Right now, a fellow named Randall Mills from Blacklight Power, that's what he's doing. He's doing the Grinnell experiments and making like it's his own. And it's a shameful thing. He's raised $80 million, and now he's settled in on capacitive discharges underwater.
Okay, so I guess the particles that you port from a quantum sphere, do they have any particular toxicity that we should be worried about if we were to get some?
I think so. I'd like to tell you about my experience. In 2010, no, it was 2009, summer of 2009, I was grinding these powders by hand with a mortar and a pestle, and using my right arm until it wore out. And I lost partial use of that arm for about 4 months. I couldn't coordinate throwing a baseball or...
Do you think that was an ingestion or an exposure thing, or do you think it was just using your shoulder a lot?
I wasn't using any rubber gloves. It was all over my right hand.
Right. Okay.
So I think, yeah. So then when that happened, I built a hood and I isolated it, and I never had a problem again. So you don't have to be great. I mean, I built it in the garage with just rubber gloves and a fan.
Yeah, well, we have hoods, but I am quite aware that nickel particularly can be really unpleasant.
When you get to the nickel from quantum sphere, it's much more dangerous, I believe, than my materials, which are basically inert rocks of zirconium oxide with nickel in them, but the nickel stays in them.
Did you read Bob Higgins's material processing approach?
No.
Okay. Well, so he's taking nickel carbonyl nickel and processing it, sintering it, and putting ferrite, iron oxide, Fe2O3, into it in such a way that it's kind of like in extremely small quantities on the surface. It basically looks very similar to, in his understanding, to SEM images of Rossi's early reports, and effectively they're nanometric structures, but grouped into a foam. It kind of makes a cake, and then he grinds that down into micrometric clusters, which are extremely porous and contain this activated iron oxide on the nickel. And his approach that we will be exploring is to look for the photon signature, which he believes will be very low energy. So he's designing a reactor, and I will likewise, that will have at least part of the wall very, very thin to allow low energy photons to come out. I don't know if you're aware, but we seem to see gamma from the Celani wires when it goes through a phase change, when we recharge it with cold hydrogen, and there's like just a spike, and it seems to be repeatable, but we've had to recondition those cells, and we're waiting until, well, actually we're waiting for 2 new glass tubes, and then we're going to rerun those experiments, and we've got a decent scintillator and spectron, a full setup to analyze it. So his reason for doing that is that these heat thermal signatures can be offset from the events that trigger them, and so and he wasn't looking to trigger with discharges. He was looking to trigger with just thermal temperature points or gradients, and so he's going to look for this gamma emissions. But you said that in your paper that you didn't really see any gamma emissions, but you did explain that the side of your reactor vessel was quite thick. Is that right?
Yeah, the reactor vessel was probably, the wall thickness was 6 millimeters. That's pretty thick for, steel. And it was rated at 1500 psi, and but basically it could probably go to 5,000 without any problem with the safety margins. But when you say you saw gamma rays, I will guarantee, with everything I know, that you saw gamma rays, but you didn't see gamma rays commensurate with any heating. You just saw bursts of some countable number, but they certainly weren't at the 10 to 12 photons per second coming out of that.
I don't know. You can look at our video of one of the events that we recorded. It just happened to be repeatable when we recharged the cells. And
what do you know about phase changes? I mean, I'd just like to point out this is very understandable, but most people don't know what a phase change is.
Well, I mean, maybe a state change. I can't remember the specific figures, but it is recorded in our Gamma blog in quite some detail. But essentially, it went from one temperature point below what we see as the kind of in the differential cells we did in the US and the EU. They both kind of switched on at around about 179 degrees and started producing, or seemingly producing, excess heat, and it kind of like stepped up from that point onwards. And essentially it was running at over 200 degrees, and when you imagine the can, the mini can with the hydrogen in it, is releasing, it has just around about 1 bar in there, and we're raising it to 3.5 bar. You've got the gas expanding, getting colder than room temperature, coming into the cell and knocking it through that 179 degrees, and then it's suddenly, because it's directly heated with electricity, it's going back through that state change. So I don't mean phase as in to liquid solid, that kind of thing.
No, it is a phase change. It's a solid phase change.
Mm-hmm.
So you wouldn't notice it. Like iron goes through the Curie point, and you don't see any change in it, but it's a local rearrangement of just a slight rearrangement, which is a phase change. But when it goes through the phase change, what most people don't know, and this is what I learned studying superconductivity, every phase change of every material, when it's going through it, things get chaotic for a degree or two. And the vibrational modes greatly are enhanced, which means the hydrogens, which are in the middle of all those, they really get enhanced going through a phase change. So it's very plausible that you would see some kind of LENR event as you go through a phase change, because that's when there's a maximum motion of the hydrogens.
Well, I mean, at that point you can't detect excess heat because we've just filled the cells up with fresh hydrogen. And the other question is, in that fresh hydrogen, it's going to have some deuterium. Is that playing a role in those momentary events? Does it get burnt up? I don't know. Is there something going on?
Are you familiar with the Mizuno work?
Yes, I am, and that is also part of what we're going to be moving forward with. We've had to assess what we're doing in light of that very methodical work that he's done. I assume you're referring to the gas phase recently reported work, which was also reported at ICCF 18 in draft as a poster.
Yes, but I was really excited about his 2006 work. And he did the simplest experiment in the history of LENR, and he made claims that he was getting bursts of neutrons, but nobody ever took him up on it. But I did. I built the equipment at the National Magnet Lab, and I reproduced his experiment, and I got bursts of neutrons from just deuterium gas in a 1.0 Tesla field. Just a B field and deuterium gas. No palladium, no nickel, no anything. And that was repeatable. So there's something very, very incredible about magnetism and hydrogen.
Well, I think at ICCV 18 and also with Constant and Mail, although like I say, I don't read German, so I'm trying to get it translated. I think it's something that with deuterium specifically, you can magnetically align it such that the ability for the Coulomb barrier it goes to zero effectively, and that you can just knock them together basically. There's like a point, and it's never in the same place if you've got particles together. And if the hotter they get, the further the less likely they're ever gonna impinge on each other. But when you get it in a condensed state, and then you can align it, you basically get it so that this similar, they kind of attract rather than, or not. There's just no repulsion, as it were. I don't know. Like I say, I'm a facilitator.
Well, I think you and like many others fell into the trap that it's DD going to helium-4.
Well, no, I don't know.
There's so little evidence for that. It's pathetic.
Mm-hmm.
The evidence for anything nuclear is absolutely microscopic compared with the heat that's being seen that doesn't seem to be related to radiation. So I think you have to be prepared to get outside the metaphor of fusion altogether and saying, this is a magnetically inspired effect, and I don't know why or what, but that's what you have to, I think, cling to, because that's what seems to be coming to the fore now, as the DD going to helium-4 people die out. It was thrust upon us, because Pons and Fleischmann found excess heat. They said, well, it's more than chemical. Well, then it must be fusion, which was probably a great disservice to everybody involved.
Well, I guess time will tell. So I think much of what we've discussed is covered here.
What's your opinion of Defcalion?
Sorry, what?
What is your opinion of Defcalion?
Well, in the blog I've just written, I had discovered from a picture in Max Lewin's picture collection from the day he visited them in the test last year, that they were using a 575 watt neon tube power supply, producing 24,000 volts at 22 milliamps, I think it is. It works out at roughly 537 watts or 38 watts, which is why you would imagine it's rated to 575 watts. There doesn't seem to be any accounting for the power coming from the arc, and I posited a question during the live demonstration that Matt put forward to them, and he Hadjikristos, I think it was Hadjikristos, said that it was a 20% duty cycle. So you can imagine like something like 115 watts or something was the input power there, but it's a little bit hard to judge that, and what was the switching circuit that they were turning that on and off with, and is there a current surge that's built up, is more power delivered? The average power might be 575 watts, but if you only got it on a 20% duty cycle, do you actually get 1/5 of that power? I don't know, and because it's high voltage DC, and the way it was done, it's very difficult to assess what that was. So I have a question there. I have a question about back pressures. What I do know is that they did allow Mats to use his own equipment, which was rudimentary, but he did have a multimeter with him, and when he tested one of the power lines, he tripped the power to the whole room, as it were, and the experiment effectively momentarily shut down. So at least whatever was being shown was actually happening at that point in time, and the whole thing wasn't a fabrication. So there's that. People that I am aware that have visited Defcallion say, well, yes, it's controllable, it happens, but they've never seen it happen for more than, say, 4 hours or something like that. And the argument there is that the spark plugs burn out, and yes, we know spark plugs burn out if they're getting very hot. And I think that if you've got a plasma of hydrogen, you're going to get something like 15 to 19,000 degrees in the actual plasma, as the plasma reforms to hydrogen atoms, and then the hydrogen atoms reform to hydrogen molecules. So there's a very good chance that they're going to be having, a meltdown of their electrodes. But I'm still confused, because sometimes they're saying they're using a glow discharge, and then sometimes it's an arc, and I don't know. So there's those elements to it. There is some chatter which I don't know all the facts behind, but I think their problem predominantly is marketing. They went for a license model which wasn't really acceptable to people, and I don't know whether they have sufficient funding to maintain operations, but that is pure speculation.
Well, my experience is they haven't been in Canada in a year. They left last April and they haven't been back. They don't say anything about that. Their lab in Milan, where they did the ICCF-18, those people are suing them. So they've got, there are people without a country. They don't have any money. They don't have any credibility. National Instruments, who was, giving them all this equipment and support, absolutely fired them and said, "You are not welcome at National Instruments ever again." So I think they have zero credibility.
I think it could come down to finances. Are the people in that lab suing them for back pay, or are they suing them because they were defrauded in some way?
The people who ran that lab gave them over 800,000 euros.
Right, well, there you go. They're suing them for money. Their problem, as far as I can see, they didn't turn up to MIT, and, I don't think that's probably because they didn't want to. I think that's probably because they couldn't afford the flights, if that's the case. I think they're probably that poor. And so it's unfortunate because, people who seem to be respected said that they've seen it work. I don't know. They're not disclosing the actual nature of the internals of the reactor, and there wasn't dry steam fully assessed, and the flow rate of the steam wasn't fully assessed in the live test. And until they can afford to do another one, and that's not going to happen if the lab's been basically shut down, then what do you do?
I actually think Captain Christoph has been fired. I don't think he's with them anymore.
Right. Well, we've got an opening if he's willing to earn nothing.
I can pay an equal amount.
Oh, well done. You see, the beauty of being a not-for-profit is that when you don't have any money, you just stop work until you do. You haven't stopped your research, it's just paused. You're doing what you can to take things forward. So, most of everything that we've done has come from, the people in the project's resources and their passion. And we've had very sizable contributions in kind. And an example would be Stoyan's work that he's just done. And we just need to try and make best use of the equipment whilst we have it. We have one proven or semi-proven active component in Celani's wire. We have the potential to make simple reactors where we can produce active component in the same way that Mizuno has just demonstrated with his recent publications. And we have the powders that have been processed by Bob Higgins. also, Alan Goldwater is starting with nickel nanofoam, nickel micrometric foam, like this type you would have in a battery kind of electrode. And he is processing that, but we will run a blog on his work soon. But he's discovered some interesting things about that foam, which might have a positive effect. But he's kind of like merging Def Callian's work with Celani's work by taking copper and fusing it and oxidizing it on the surface of the foam. And I think there's good merit in that, because if you look at Takahashi's work, where they were using, I think I'm right in saying this, no, the stuff done at Technova recently, they used nickel only. It was silicon included nickel, and they got excess heat of 1 level. And when they did a proportion of copper, nickel, silica included, they got 10 times the level of excess heat. So, you know, they're kind of feeding back to Celani now, who's wrapping his stuff in glass and seeing, which is something he did a very long time ago and couldn't explain why he was getting enhanced excess heat in older experiments, but he's seems to be seeing something there. So I don't know, there's a bit of cross-pollination going on there. But you said in one of your experiments that you did try copper in your particles.
Well, I was one who suggested it to Celani. I discovered a resource from Poland, Romanowski, who had shown from a theoretical basis that nickel-copper alloys were very good at hydrogenation. And so I said to Celani, you should try this alloy. And I ordered some, and it did a good job. It wasn't, you know, any better than anything else, but it was worth examining, I think. You should look up the Romanowski paper. It's referred to in my, I think I referenced it in my appraised.
Yeah, I might have looked at those a long time ago, but and is that something to do with spillover, or is that not?
Yes, it was. Yeah.
Yeah, I think I did read it. It's I've got a vague recollection.
That's where it all started. I sent that to him in 2010.
Right. So I guess where we are then. Okay. Did you take any SEM images? I think you referred to some in your report, but
yeah, they're shown in my report. Takahashi actually made them.
Okay.
He did TEM as well, and the TEM couldn't have been clearer. It was a beautiful demonstration that the particles were there. I was so glad that I sent it to him.
Brilliant.
And that was the material that material that blew up on me. It burnt up my ceiling. You know, it was a flamethrower. It was a terrible thing. 30 grams, 20 of it went out into the atmosphere, but 10 of it stayed behind, and that's what I shipped to Takahashi.
Right. Okay. So
He said it gave more energy than any sample they ever ran.
What was the nature of that material?
It was finely ground.
Right. Okay.
The one that the macroscopic, nanometrically it was the same, but the macro grains were not 75 microns, they were 15. And that's what caused the explosion, we believe now.
Right, okay. And do you think that's a particular resonance issue, or?
Yes, there's people at NASA who really believe in plasmatron resonances, and that happen between 15 and 20 microns. I never knew anything about it. I just heard about this 6 months ago, but they're very serious about it.
See, my brother's, he's developed a thing called a resonance engine. He's very keen on resonance, and as far as I can see from the video, they're taking a lithographic process at NASA, and they're creating a plate that has a load of different size structures and maybe shape structures, and then exposing that to the reaction environment and then seeing which responds the quickest or most interestingly.
That's the guy Zawadny, right?
Yeah.
Yeah, that's his boss, Dennis Bushnell, is absolutely bullish on this 15 to 20 micron size, and that's just where my sweet spot was in the power that blew up. But I didn't learn about this until the program was over.
So do you think that's like a harmonic?
Yes.
It's a harmonic of the nanometric scale.
I do.
Yeah. Okay. So one's playing off the other. So essentially, the micrometric scale provides a kind of resonant reservoir for stimulating the nanometric features.
I think it's a resonance on top of a resonance. I don't know how to explain it other than that.
Or maybe it's a magnetic resonance in the micrometric that stimulates a, cross correlation. Or is this what you're referring to when you're saying? How do you refer it to? Micrometric. Not you saw anharmonious oscillations.
Anharmonic oscillations.
Right.
Those oscillations can be very, very large, but also cooperative, so that the magnetic storms can get started, but macroscopically they can tie themselves together, just like the atmosphere can form a tornado or a hurricane, which is a self-focusing event, but nobody knows how it started. And I think magnetic storms is what's happening in these materials, and whatever you can do to improve upon the storm characteristics, the better you'll do.
In terms of surface processing, I've seen some papers that are using nickel that's been vapor deposited on, or maybe chemically deposited onto silicon, and they're using laser ablation, and the nickel wets under certain levels of energy and exposure to the laser, and it forms pillars and gives you silicon black, which is much higher efficiency for a solar panel. But I was considering whether the same technique could be used to create specific structures, and when you look at these things, they kind of look like a dog brush, if you know what I mean, a big flat thing with things coming up, and it looks almost like ideal. These are kind of like big waggly tuning forks, and if you can get them the right shape, then you're creating nanostructures that are long and thin cylinders that are supported by a rigid base. And if you could get it right, you could actually have a roll of something coming off, which is then laser ablated, and it's all done inside the sealed unit, and it just rolls up onto a spool, and that is your reactor core.
I think there's a lot of lore and rumor and innuendo that Rossi does have some kind of complex structure that he got from some old fellow who was probably making catalysts for some hydrogenation process. And that is the big secret. So I do believe that there is a nanostructure in the a microstructure that's important, but I don't know how to get there.
Okay, so when you were doing your tests, if we were to get the powder that the powder that you saw that blew up on you when you ground it down more, you've got some of the unground material left lying around somewhere.
No, but I can find out what it was, and I probably have from a different batch similar things that I could pass along.
Okay, well that would be very useful. I have a question here from Bob Higgins. He's asking, what are the maximum safe temperatures before you saw breakdown and sintering?
Breakdown and sintering? I didn't see any up to 450 C.
Okay, so that's fine. At what was the longest period you saw LENR activity?
I see sintering at 800 C.
Well, yeah.
I mean, I accidentally did it, and there was 800. I went, oh boy, and it was just a slag after that.
What length of time was the maximum time you saw active LENR? Because you seem to be shutting down experiments to look at the ash quite regularly, as far as I could read.
The longest I let it go was 38 days. and it didn't show any sign of decreasing with 0.6 degrees delta for 38 days. But I said, I've got to do another experiment, so, I was always hoping I'd get something way better, so you just keep going from one to the next.
Okay, and you've had a reactor meltdown, which you've described.
No, it wasn't a meltdown, it was an explosion.
It was an explosion. Right, and that was in a very high pressure vessel.
It was, but it had a neck on it with an O-ring, and it just blew the O-ring in the thermocouple or the RTD out. And when I, put it back together and I hung it upside down and put weights on it, it would have taken at least 3,500 psi to do that, to start it. And it shot out instantaneously. Something happened to raise the pressure to over 3,500 psi over a period of minutes.
Were you in the room at the time?
I was 3 feet from it. It was next to my head, but it was facing tangentially to me. And I was on the phone talking to a guy, and "Bro!" and I screamed and ran behind a building. And it was a big deal.
In your typical reactor configuration, how does the powder temperature compare to the reactor vessel temperature?
Well, you would put the powder in, you'd bake it out for a day just to make it, get the water vapor out of it. And then you'd add hydrogen, and the temperature would go up as high as 200 C.
Yeah, but that's just the actual...
that's just the exothermic reaction. Then it would cool back down.
Yeah.
And then come back to room temperature, plus, within a degree or two. My highest one that stayed up was 2 degrees C, for 4 or 5 days before I turned that one off.
Okay. And you talked about repeatability. Did you identify anything that poisoned your LENRs, i.e. you did something that stopped them from working?
Well, titanium.
Okay.
If you think heating works, negative heating is... That's why I say it's not heat. There's an event going on that supersedes heat.
Right.
Like the anomalous is an example of that, but the titanium, giving you negative heating that's new physics, and I don't pretend to know how or why.
Okay. Did you see anything really that in your ash? I think you've discussed some in the paper. Did you see any?
Thorium.
You discovered that wasn't there before, or?
No, it wasn't there before.
Right.
It came into play as a part of the tumble mill, which is neoprene, and believe it or not, they use 2% tellurium to cross-link neoprene. It's just in the rubber. So that would come out in my analysis.
Okay.
I don't think it affected the working of anything.
Right.
Example, the ball bearings. If you used iron, steel ball bearings, they would rust, and that wasn't good. It actually turned the powder brown. You did it in the summer when it was moist, so I had to use a nickel-based ball bearing.
When you were looking at the quantum sphere particles, you said that they had problems with vacuum equipment, and that you solved that by using Teflon bearings.
I did not solve it.
You did not?
I never solved it. I didn't come close to solving it.
Right.
My valves were metal seats and metal plungers.
Mm-hmm.
Another person named Snoswell from Adelaide, he found out that if you had a Teflon plunger, you could crush the powder against the seat and make it stick. And I didn't know that. It was terrible. You couldn't get any vacuum at all. That's why I started working with it. I go, I can't seal this stuff. And then I learned 6 months later that he figured out how to do it. So.
Okay, so are those standard components that you can buy with the Teflon seals? Yeah,
you can buy them. I didn't know that.
Okay, well that's something to bear in mind if we take that approach. I mean, if the activated ferrite nickel nanometric micrometric clusters, if I've got that right, that Bob has created yield sufficient excess heat. I mean, his whole point behind creating those is to make it very safe and also make it sure that there's no chance for it to become airborne, as it were. Precisely for these sort of reasons, and just a piece of wool or something in the way. I mean, some sort of fine filter would be sufficient to stop those micrometric.
You can't filter it. You absolutely cannot filter it.
No, Bob Higgins's micrometric foam.
Yeah.
Yeah.
But the quantum sphere, you can't filter it. There's never been a filter that can do it. It's just too small.
It sounds really unpleasant. Okay. So there's a specific question here from Bob again. Is based on your experience, do you believe the Lena output to be kinetic, phonon, or photon emission?
I think it is related to a new magnetic condition of the universe. I don't know, how it comes out. Is it kinetic? It doesn't have to be. It could be cooling. So I don't know the answer to it. I'm just saying it is not fusion. There's no way. It has nuclear overtones in secondary channels, but basically this is not a nuclear process.